Now we are going to move on to section 6.6. This is the section on critical points and second derivatives. We've talked a lot about how to take the first derivative of a function from Rp to Rq. Now we're going to talk a little bit about second derivatives. And we'll talk just about second derivatives of functions from Rp to R. You could glue them together the way we saw in section 6.5, but that would be really obnoxious. So we're not going to do that. So here is the first theorem. Let's let X be let's say it's an open subset of Rp. Because we want the gradient to be well-defined. We want the first derivative to be well-defined everywhere, and we've only really, so we do need the derivative to be unique, and we've only really seen that in open sets. C is a point of X. Because X is open, that means it's an interior point, and let's let F be a function from X to the real numbers. You can put it together for yourself if you ever need a function from X to Rq. I'm very sorry if that does happen because that's just notationally nasty. So let's suppose that the gradient of F exists. Actually, we need more than that. We need that F is differentiable. So the full derivative exists. So gradient of F of X exists for all X in our domain X. Now, the gradient, that's a function. The gradient of F, that's a function whose domain is X and whose range is Rp. So let's suppose that grad F is differentiable at C. So that is the derivative of the function grad F evaluated at the point C, and I really don't want to have to keep writing that over and over. So let's name that A. That thing exists. And then there's a conclusion that looks an awful lot like the formula for derivatives. Then there is a function eta whose domain is X, whose range is the real numbers, just like our function F. And as usual, eta of C is 0 and eta is continuous at C. That means that eta has to be small when X is near C in particular. And we've got the following conditions. We've got that F of X, we've got F of C, and then we've got df of C. We remember we assume that exists everywhere, evaluated at X minus C. And then our next piece is 1/2 the inner product of X minus C with A. A is a linear operator evaluated at X minus C. And then last of all, we've got the norm of X minus C squared times eta of X. So this is an awful lot like Taylor's theorem. We've got our constant term f of c. We've got our linear term, a linear function of x minus c. We've got our quadratic term, inner product of x minus c with x minus c, and you've got to have a linear function in the error, and then you've got a 1/2 out front, and then our error term here, it's smaller than the norm of x minus c squared, so it's smaller than our quadratic term. Now to prove this, we're going to define eta in the obvious way. I don't really feel like writing it out. You solve the above equation for eta, and then you write out the piecewise defined function. And we must prove that eta is continuous at C. And now, since X is open, we have that there is some ball centered at C of radius r contained in X for some positive radius. And so we only really need to show that eta is continuous on that little ball. Since we're trying to show continuity at C, we can always suppose delta is less than our r. So now let's let X be in our ball centered at C of radius r. Let's say it's not the middle point. We know what's going on at the middle point. And recall this is contained in X. And now we are going to define some auxiliary functions. So first off, gamma of t is c plus t times x minus c. So that means gamma is a function from the real numbers into Rp. Gamma of 0 is c. Gamma of 1 is x. And let's let g of t be the everything except eta bit at the point gamma of t. So that's f of gamma of t. Then we subtract off all the other stuff. F of c, then inner product, then df of c of gamma of t minus c. Then we subtract off our 1/2 t squared. Then we've got our gamma of t minus c, a of gamma of t minus c. And then let's simplify this. F of gamma of t minus f of c. Well, there's not much we can do with that. But when you write out what gamma of t is, and you remember that df of c, that's the inner product with the gradient, you've got t times the inner product, gradient f of c, x minus c, and then 1/2 t squared, x minus c, a of x minus c. Now we're going to notice that g of 1 minus g of 0, you plug in 1 for t, you get f of x minus f of c minus df of c at x minus c. Whether you write this with a gradient or a df does not matter too much. And then our 1/2 x minus c, ax minus c. This is all the g of 1 part, but if you plug in 0 for g, you get f of c minus a bunch of zeros. So now, notice that this is precisely the thing we're calling x minus c squared times eta of x. So we want to show that this thing, this g of 1 minus g of 0 is small. Now we're going to want to differentiate g, and it's really this piece that is going to be interesting. The rest of it you know how to differentiate. By theorem 6.5.13, the derivative of f composed with gamma, that's what that is, at the point t, and let's say of s, because the derivative of f composed with gamma at the point t is a function that's df at the point gamma of t, composed with d gamma of t, all of s, and that we can write as the inner product of the gradient of f at gamma of t with then the derivative of gamma, since we have an explicit formula for that, that's s times x minus c. So if we write this in terms of, we understand f composed with gamma prime of t, that, remember, df composed with gamma is the linear operator that multiplies by f composed with gamma prime. That's how we relate these strange new linear operator derivatives to the number derivatives we know and love. That is going to be the inner product of gradient of f at gamma of t with x minus c. Notice this exists if t is between 0 and 1, because gamma of t is it's going to be in the ball centered at c of radius r, and the norm of gamma of t minus c, that's going to be in fact strictly less than the norm of x minus c. So our function g is continuous because it's differentiable. It's differentiable everywhere, so of course it's continuous. So by the mean value theorem, there is a t between 0 and 1 such that we've got our x minus c squared times eta of x, which we said was g of 1 minus g of 0. That's g prime of t, and we've discovered that g prime of t is gradient of f at gamma of t, inner product of that with x minus c. We have a couple of pieces that are showing up from our explicit terms with t in them, a gradient of f of c with x minus c. And then we subtract off t times x minus c, a of x minus c. And now what we're going to do is we're going to use our fact that the gradient of f is differentiable. So the gradient of f of gamma of t, that's gradient of f of c plus the derivative of the gradient of f, which I didn't want to write out, plus a of gamma of t minus c, plus, now because this is differentiable, we've got a gamma of t minus c times some function f of gamma of t. That's all from our definition of differentiability. And then we have to subtract off inner product gradient of f of c with x minus c. And then t times x minus c, a of x minus c. Now, this term here is going to cancel out with the gradient of f of c when we inner product it with x minus c. That's not an issue. So what we're left with is the inner product of a, now what's gamma of t minus c? Gamma of t minus c is t times x minus c, x minus c. And then we've got our norm of gamma of t minus c. Let's make that a t times x minus c. And then our inner product of f of gamma of t, x minus c. And then we're still subtracting off the second part. I'll play a little fast and loose with the order. We put them in real variables. It doesn't matter. And then we see you can move the t, this t here out of the linear operator and then all the way out of the inner product. So these two terms are going to cancel. And we're left with a norm of x minus c, and then a t, and then an f of gamma of t, x minus c, inner product. So we can write down what eta is. So eta of x is exactly that divided by norm of x minus c squared. You've got a t inner product of f of gamma of t, x minus c, divided by its norm. So we've got that eta of x, the norm of that thing, or no, the absolute value, because remember, f is a real valued function and therefore big F and eta are. T is less than 1. X minus c over x minus c is less than 1. This is at most the norm of f. Big F is coming from the gradient of little f, so that one is a vector. Big F is continuous at c. Big F of c equals 0. Eta of c equals 0. So I think I will let you trace through the epsilon delta steps to see that eta is continuous at c. And that is all there is to that. I'd like to say a little bit more about this linear transformation, big A. That's the derivative of the gradient of f before we move on. So we can write out an explicit formula for what A is. This is from a theorem from section 6.5. We've got that if x is a vector, A of x, which we remember is the derivative of the gradient of f of x, at c, and then you plug in x, and our theorem gives us a nice explicit formula. That's the sum from j equals 1 to p, because our function gradient of f has p parts. Sum from k equals 1 to p, because our domain is our p. And then partial k, and then we put in the jth component of our function we're differentiating, which in this case is partial jf of c, and then we multiply the whole thing by xk, the kth component of our vector x, and then we have to put the jth unit standard basis vector in. So if we take the inner product of y with a of x, which is often written ax, that's, remember, the jth component of this thing is just whatever is attached to ej, which means this piece. So this is just sum from j equals 1 to p yj times sum from k equals 1 to p. Let's put our derivatives together. Partial jkf of c xk. Or we can put the yj and the xk together. And I will point out to you that if you just switch the j and the k here, everywhere you see a j, you write a k, and vice versa. It is the same thing. J and k are dummy variables. They're just indices of summation, and it doesn't matter which one goes with x, which one goes with y, as long as you're consistent. Now, by a very early proposition, if all of those second derivatives, if they all exist not just at the point C, but in a neighborhood of C, if they exist and are continuous, then partial jk f of c is equal to partial kj f of c. The mixed partials, it doesn't matter what order you take them in. So the inner product of y with ax, let's write that last sum. Except instead of having partial kj, I'll write partial jk f of c. Then I'll put the other two in the other order, xj yk. And if you work through this, this is the inner product of x with ay. So A is Hermitian. Like the matrices you spent so much time on the homework. This matrix that shows up in our second derivative is a self-adjoint matrix, is a Hermitian matrix, so we can apply your last night's homework to to this matrix, to this linear transformation. So here is what we are going to do with our Hermitian linear transformation with this lemma. And we're going to prove the analog to the second derivative text. So let's let X be an open subset of Rp. C is a point in our open domain, f a function from X to R. And let's suppose that C is a critical point. Of our function f. And we're going to suppose further that the conclusion of lemma 6.6 and all the stuff coming after it, all the stuff what we just wrote down is true. That there is a function, a Hermitian linear function let's call that, and a linear from Rp to Rp and Hermitian. And an eta going from X to R with eta of C equaling to 0 and eta continuous at C, such that f of X is equal to f of C plus. Now, because it's a critical point, we know that f is differentiable at C, and so its gradient must be 0, so we're not going to write that part. We're going to write 1/2 inner product x minus C, a of x minus C, plus x minus C squared, eta of x for all x and x. And let's know when this is true. By all the stuff we saw on the we saw a minute ago. This is true if each second derivative exists in X and is continuous at C. This is true. And for those of you who are up on your matrix theory, A is the linear transformation. AX equals, you multiply by a matrix partial 1, 1 f of c, partial 1, 2 f of c. Actually, down to partial p1 f of c. Partial 1 p f of c, then across partial p f of c. Anyway, that matrix times the vector, which is just x as a column vector. And this can be important because we, or at least people who are really up on their linear algebra, are very good at manipulating matrices, and in particular finding eigenvalues of the things, which is what this theorem I'm about to write down is going to want us to do. Then if you can compute the eigenvalues of A, which you will be able to do, should be able to do after most linear algebra classes, if all of the eigenvalues of A are positive, then F has a local minimum at C. And if all of the eigenvalues are negative, then F has a local maximum at C. And there's actually a third possibility where we have information. In the one-dimensional case, either your second derivative was positive or your second derivative was negative, and if your second derivative is 0, you didn't have any information. But in this case, there's a third possibility where we know something. If at least one eigenvalue is positive, and at least one eigenvalue is negative, then F has a saddle point. So definitely does not have a maximum or a minimum. It definitely has a saddle point at C. And as a remark, the only situation where none of these three are true is that if at least one eigenvalue is 0, and the rest have the same sign, that includes the case where all the eigenvalues are 0. This is like getting your second derivative is 0 in the one-dimensional second derivative test. We just say the test fails. And I will point out in the one-dimensional case, this matrix big A is just multiplying by F double prime because you've only got one dimension. So the eigenvalue is just the value, and it's either positive or negative or 0. So now let us prove this, and we'll start by writing down all the stuff you worked out on your homework last night. A is Hermitian. So if you remember your linear algebra, what this amounts to is there's an orthonormal basis of RP that consists of eigenvectors of A. If you don't remember what all of those words mean, what you proved last night is that there is a set of vectors in RP such that each of them has length 1. Any 2 of them are orthogonal. And each of them is an eigenvector, meaning A of UK is lambda k at UK for some scalar lambda. And if X is in RP, then we can always write X as this inner product of X with UK times UK. And those of you who remember your linear algebra know that this means that the U's are an orthonormal basis, and in particular, a basis for RP. You may remember that all bases have the same number of elements. This means, in particular, N has to equal P. Yeah, we will not use that fact, but for those of you who remember for linear algebra and think it's very strange that I'm using N instead of P, you're correct. In some sense, I should be using P, but I don't want to assume that we remember linear algebra that well. So since we don't need this fact, we won't bother proving it, so I don't really want to use it. So let's write down a couple of consequences. So if, let me call it Y is in RP, then the norm of Y, let's go ahead and square it. We've got a bunch of squared norms showing up in our theorem, and it's easy and our life is easier if we just don't have to keep writing square roots all the time. That's the inner product of Y with that sum. And now we remember that the inner product is bilinear. That means it's linear in either of its two elements. So we can break this sum up. And then we can go ahead and pull out the inner product of y with uk. That is just a number. So we can write the norm of y as this sum of squares of inner products. And also this quantity that shows up in our theorem, inner product of, well, I don't feel like writing x minus c, which is why I am using a y. Y is x minus c. That's the inner product of y with a of. A by assumption is a linear transformation, so we can pull the sum and the constants out. And then we're going to do two things. We're going to pull the sum and the constants out of the inner product as well, leaving the inner product of y with auk. But auk, remember, is just lambda k times uk. And then we pull the lambda k's out. And we get our yuk's squared. And now in the case A, if all of the eigenvalues are positive, then we can just take the smallest of them. There's only finitely many of the lambda k's, so one of them must be the smallest. Since they're all positive, the smallest of them is 0. So inner product of y with ay, that's greater than or equal to this sum. We can replace the lambda k by a lambda. The yuk is squared. It's the square of a real number, so it's of course non-negative. And then we note from before, hey, that's exactly, you can pull the lambda out of the square, and hey, that's exactly lambda times the norm of y squared. And then in the other case, B, why don't I call it negative lambda is the biggest of your eigenvalues. That is the one closest to 0, the one with the smallest absolute value. That is negative. So exactly the same argument, inner product of y with ay is going to be less than or equal to negative lambda times the absolute value of y squared. And now to prove parts A and B, we're going to use the fact that eta is continuous. So we're going to let delta be a positive number, or such that if x minus c is less than delta, then we'll say lambda, which in either case is positive, is greater than eta of x minus eta of c, but eta of c is in fact 0. So this is eta of x. So in case A, f of x, that's f of c, we'll write down what we've got above. And then this is greater than or equal to, well, f of c will leave it as the same. And then this is 1/2 lambda norm of x minus c squared. And then eta is less than lambda. Eta is between plus or minus lambda, so we'll subtract off. Sorry, I wanted this over here to be a lambda over 2 minus lambda over 2, and then the x minus c squared stays in place. That's greater than or equal to f of c, or in case B, f of x less than or equal to f of c plus 1/2 lambda x minus c norm squared. Sorry, this one is minus plus lambda over 2 x minus c squared, which is less than or equal to f of c. So we've got a local minimum here and a local maximum here. The proof of part C is going to be simpler. We're going to let uj, uk be such that lambda j is bigger than 0 and lambda k is less than 0. Then fj of x, of t, sorry, that is f of c plus tuj. That's f of c, and then lambda j over 2, inner product of uj with itself, and a t squared. And then uj, remember, is a unit vector, so this is 1. And then we add onto it a t squared eta of tuj. And as before, fj has a local minimum at t equals 0. Same argument, fk has a local maximum. You write out exactly the same equation with k's instead of j's, and then you notice that lambda k is negative, so your t squared term is negative. So f has a saddle point at C, and that completes the proof.